So it's a pipe. That's it. It's pipe. Don't think of it as something very, very complex. Especially in the ideal sense, the best way to imagine this thing is simply a pipe. So we have flow in, and we have flow out. Often used for gas phase reactions. And again, as you're going to see, this requires the least amount of volume to reach a certain conversion. So if you're comparing a CSTR with a PFR, this one requires less volume. Another nice advantage of this is for giving pressure drop considerations, which we'll talk about in the class. You can make these pipes pretty small. So what's a system that has a bunch of little pipes flowing through a big region that has a different material on the outside? A heat exchanger. So if you've got a strongly exothermic reaction, a lot of times what you're going to do is basically take what looks like a heat exchanger and you're going to flow your reactants through the middle, and then you're going to surround this with something to essentially remove the heat, usually water, right? And so you're just heating the water with the exothermic nature of this reaction, and you can use that hot water elsewhere in your system to try to recover some of the heat. So PFRs work nicely as the interiors of a heat exchanger in order to remove heat from a process. Even though you can do that, it's still harder to maintain temperature control of this unit than it is a batch or a CSTR. Because what are we missing here? There's no impeller, right? There's no artificial ability to mix. So you're going to get some mixing due to turbulent flow, like we'll talk about in a second. But you really don't have the ability to mix. And so you are going to have, and this should go without saying, right, that this concentration is not going to be the same as this concentration. Right? The concentration is going to change as you go down the bed of the reactor. I'll say bed a lot. We are going to talk about something called a packed bed reactors. It's just because usually when these are used in industry, you fill it with a solid called a catalyst bed. But if you hear me say bed, just think tube. It doesn't make a difference. Okay, so rather than trying to do the species balance on the whole thing, let's start with a little section here. Make sure, yeah, he uses Y, so we will too. We're going to call this Y, and this we're going to call Y plus delta Y, right? So this should look familiar to you guys, what we're setting up here. So within that small region, we have flow in, which remember is changes with Y, right? And then coming out, we have flow at Y plus delta Y. And so what is the volume that we have here? Simply the area, the cross-sectional area, times that differential length, delta Y. So if we solve the material balance on just this small section, you get that the flow, which remember is a function of Y, is equal to minus the flow out in that region plus the generation in that region is equal to 0. And again, we can put this in terms of delta Y and an area term, so we will. And so you get the area times the rate is equal to these two flow terms divided by delta Y.
What is the area? Capital A, area?
The cross-sectional area, yeah. All right, that makes sense, right? Area times length, volume. So the design equation that we're left with is it's similar to what we had for a batch reactor. What's the difference?
This doesn't change with time.
Yeah, instead of this being dt, it's now dv, right? And so on the right side, we also don't have it multiplied by volume because that's now what we're integrating across. Or that's the differential. So if I have a schematic here, and this is length, and let's imagine that we have a first order reaction. What happens to the concentration of A as I go further into the PFR? It decreases linearly? No, it decreases like this. And then remember that that looks exactly like what happens in a batch reactor if now instead of length I just change this to time.
Is this always the case?
For an no, this is for a first order reaction. If it were zero order, what would it look like? It would be a straight line, right? So this would be first, this would be zeroth order, and then second would be something like that. So no, it depends on the kinetics of the reaction. But the point is that it's very similar to what you get for a batch reactor, right? And so something that you'll see tau used for both CSTRs and PFRs residence time, right? Things aren't actually changing with time, but residence time depends upon the size of the reactor and the flow rate of that reagent, right? If I slow down the flow rate of A, does it spend more or less time in the reactor? More time. Do you get more or less reaction if it's a first order reaction? You get more reaction, you get more B, right? So it's very similar to, again, changing the time in a batch reactor. So instead of writing length here, you could have also written the residence time. The other thing to note is that I can now control residence time two ways, right? I can make the reactor, in this case, longer. That would increase the residence time, as would making it bigger if I'm talking about the cross-sectional area. Anything to increase the reactor volume increases the residence time. I can also, though, slow down the flow rate. So those are two ways that we can control the conversion, ultimately, of a reaction, is we can make the reactor bigger, we can slow down the flow rate of the reagents going through it. Again, for both CSTR and PFRs. We can't do that for a batch, we don't have any flow. And then, of course, we can also do things like change the temperature. So the last one that we'll talk about is very, very similar, but we'll put it up here, because Fogler treats them somewhat differently. Not that PBR. So you've got some solid material packed inside of your reactor, and again you have flow in and flow out. Normally, what are you packing this with? Catalyst, right. Not just catalyst, though. It's important to think that the active sites of the catalyst are a minority species. Most of the time, what you're going to have is a little bit of, say, platinum on a pretty big support. And then often you'll have that mixed with support that has no metal loading. So you'll already take a material like this, might be 1% platinum on alumina, and you might mix it with 10 times as much alumina. Yeah?
So when we're looking at the chaos method kinetics in solve those equations, we usually assume that the enzyme concentration is high enough that it really doesn't matter what the concentration is. The reaction rate will proceed at the same if we were to increase it or slightly lower the enzyme concentration. Is it different in chemical industry that the rate of reaction is so much faster that we never reach that point where you hit that Vmax?
If you have an equilibrated reaction, then the amount of catalyst you have doesn't affect the amount of products you get. In other words, you've got more catalyst in there than you need, and so before you can finish the reaction, so to speak, you essentially hit equilibrium, and once you're at equilibrium, the catalyst isn't really doing anything. But most of the time, you're not operating at conditions of equilibrium. So most of the time, when you change the amount of catalyst in the system, you will get changes in the conversion. Yeah?
Is it because chemical processes require more conversion than biological processes, or is it that catalysts probably are much worse than enzymes?
No, so on a per energy basis, catalysts beat enzymes. The problem is that enzymes, generally speaking, they're just doing a very small amount. I think that was the first thing you said. It's more related to the amount of reaction you need to take place. Enzymes don't go to very, very high conversions. Whereas, of course, in an industrial setting, we want to get as much as we can out of it. You know, the enzymes aren't free, quote unquote, like they are in a biological system. But generally speaking, catalysis outperforms enzymes for systems where they're both being attempted to use for the same problem.
Aren't enzymes a kind of catalysis?
No, they are. So I'm just on, man-made catalysts. It takes a lot of energy to make an enzyme, and even then, it steals a lot of energy from photosynthesis or from respiration. So all those ATPs add up quite a bit, and it's actually more expensive to use ATPs on a thermodynamic standpoint than it is to just give it a little bit of heat. But I mean, that's not to say they don't have their purpose. I mean, there are things they can do that we don't know how to do, like low temperature nitrogen fixation. We don't know how to take into gas and make ammonia without going to really high temperatures. Catalysts do it all the time. I mean, enzymes do it all the time. So they have, where they work, and then in catalysis you have different capabilities. Yeah. Yeah, sorry. So imagine you have a support particle. It can be a few microns in size. And inside that, you might have nanometer size particles of a precious metal like platinum. And so inside that support particle, you might have a loading of about 1 weight % platinum. Even with that, you might then decide that you want to dilute that particle along with a bunch of other particles that are just pure support. So that the final loading might be 1 in 1,000 parts platinum. And so when we talk about a catalyst bed, in a physical sense, what you're most often referring to, like in terms of how does something flow across it, is you're thinking about how does it flow through the support, not through the catalyst itself. Yeah.
Why do you want to lose more support?
Exothermic reactions is usually the most common reason. Is you don't want to make hot spots in your reactor, so you want a nice dilute material so that the heat can be evenly passed to the outer walls of your tube, which is where, again, you'll have some sort of heat transfer liquid usually present.
Quick question.
Yeah.
Would you ever use this for safety purposes where you put like an inhibitor in there to slow the process?
So there are examples where,
I mean, like usually, yeah, you're trying to achieve it, but I'm just saying, like, if you were limited and you have to do a quick replacement, like, would they do something?
yeah, I mean, so answering it in a different way, rather than talking about safety, we'll talk about control, because that's usually, better. And they're often related, right? So when we guys run these in a real plant, is this all that we have? Do we think that we just flow it through the reactor bed and that's it? Or do we do anything to those products? Do we recycle them? Right? So most often you're actually going to have a recycle stream. And a lot of times an inhibitor might be a product. And that recycle stream is what will allow you to, it makes sure that inhibitor is kind of always present. So in some sense that's true, but I don't know of anybody adding a specific chemical reagent that would shut down a reaction at a certain time. It might be a good idea, but if those controls exist, I don't know of them. What's normally more common is you might have an inhibitor nearby, or you might drain the reactor rapidly if it hits a certain temperature. Because temperatures are usually where you're going to have a runaway, right? As it gets warm because it's exothermic, and that increases the rate, and that increases the rate of heat release, and that's where you get into real trouble. Yeah?
You have like a radical polymerization reaction or whatever, and you have to shut down the reactor, you go move to the storage tank. So there's like nothing to add to that tank to help quench the reaction?
Again, I mean, I'm sure that you could find an example where they might do that, but what's often used as a quench for polymerization is, I mean, one, you run at a temperature where the rate of polymerization growth is well controlled, right? And so most often I can usually quench thermally easier than I can quench physically. And the problem with a physical quench, it would be a last resort always, because separations, like we talked about a few weeks ago, are the most difficult part of a chemical process. So I really don't want to put anything in there that I've got to try to get back out.
If it was during the reaction, it's already like a last resort situation.
Yeah, that's probably true. So no, I mean, there could be examples where they throw in a quench, but I just don't know of any off the top of my head. So rather than talking about volume, as we have for CSTRs, batch reactors, and PFRs, here, the way that we'll sort of classify this is a weight, and then this is some weight plus a differential amount. So what is that weight of? The catalyst, right? Whatever that solid material is. So this is common, again, for catalysis, which is a gas-solid reaction. You can use it in aqueous phase. I mean, there are, or liquid phase, I should say, more generally. There are liquid phase flow reactors. They're just less common. Usually, PFRs and PBRs, it's a flow reactor. It's gas phase. And so remember that the reaction rate for a heterogeneous reaction, we didn't write it per volume, we wrote it moles per grams catalyst. And then of course we still had the seconds in the bottom, right? So that's why instead we write the design equation in terms of W, which just means mass of catalyst. And it's the exact same over here, so I won't go through it. What you get is, and in my notes, they use a prime whenever you're talking about reaction rates in terms of grams catalyst instead of volume. So that's what that prime is. But you see that it's the same as what we had over here, right? That instead of now dV, we're doing it in terms of the weight of the catalyst, and so it's the same reaction rate, just with a prime. So that is the design equation for a PBR is over there. Here it is for a PFR. All right, any questions about those design equations before we move on to thinking about these again, but now in terms of reaction conversion?